that can replace the rising desert areas from the coast, and it comes through predominantly in the summer months.
With over 4,000 wind machines in operation and more efficient turbines coming online every year, the San Gorgonio Pass represents a productive use of the land, and like their counterparts in agricultural production, can best be described as a series of farms, wind farms to be exact, and the crop, that is the wind, is harvested year-round. Like any other farmer, wind farmers are businessmen and women, keeping a close eye on costs, the upkeep of their machinery, and, oh yes, the wind. Though the wind machines in the San Gorgonio Pass operate year-round, the daily weather forecast gives the wind farmer the data necessary to operate at maximum efficiency. Today's machines operate most efficiently at wind speeds of 15 to 35 miles per hour. In the San Gorgonio Pass, peak months are May through August. But even in these peak months, some machines are not turning. This is due primarily to three fairly common situations. First, the design of some machines makes them susceptible to damage during very high winds, so they are shut down during these periods. Second, there are still some old, outdated machines in abandoned wind projects that have not yet been upgraded or removed. And third, some are undergoing periodic routine maintenance, while others are being retrofitted to improve their efficiency. As the wind blows, an anemometer mounted at the top of the tower checks wind speed as a wind vane locates direction. This information is correlated in the turbine's electronic brain or computer, usually found in the base of the turbine tower. The computer regulates the operation of the machine, optimizing it for maximum efficiency and providing a log of its operation. Many turbines are also monitored and controlled remotely. Here in the maintenance bay, we can examine close up the inner workings and basic components of a wind turbine electric generator. On the front is the hub, to which the blades are attached. This turbine utilizes 3 blades. Attached to the hub is the low-speed shaft, turning at the same rate as the blades. On this particular shaft, we find the braking mechanism, similar to that used on a big rig truck. Then, the low-speed shaft connects to the transmission or gearbox, which changes the speed from 45 to 50 revolutions per minute to the 1200 RPM necessary to generate utility-grade electricity. Finally, the generator itself, which converts the mechanical energy to electricity. The electricity generated in each wind turbine is transmitted through underground cables to a field transformer that steps up the voltage for transmission. A collection line connects the field transformers to a utility interconnect or power substation, like this one, the Devers substation, operated by Southern California Edison Company. Here, the electricity is added to the utility power grid and combined with hydroelectric, coal, nuclear, oil, and gas-generated electricity for distribution to Edison customers. Last year, the power generated by the machines of San Gorgonio surpassed 575 million kilowatt-hours. That's enough power to satisfy the electric needs of all the homes in the entire Coachella Valley area of Southern California. In fact, when all the wind turbines of San Gorgonio, Tehachapi, and Altamont Pass are added together, they generate enough electricity, over 2 billion kilowatt-hours, to power the city of San Francisco for the entire year. Wind plants currently produce nearly 3% of the state's electrical energy, but on the Big Island of Hawaii, that figure jumps to 15%. If wind is to play a bigger role in electrical energy production for the United States in the 1990s, 2 questions need to be addressed. First, refining turbine technology to increase profitability in areas of lower wind speeds, and second, finding more potential wind generation sites. At AeroVironment, an innovative wind and propulsion research company in Pasadena, California, state-of-the-art computer models are used to help site new wind farms. AeroVironment, founded by Paul MacCready, the world-famous inventor of the Gossamer Condor and later the Gossamer Albatross, has recently completed a 3-year program to develop a fast and efficient method of siting wind turbines, utilizing a user-friendly personal computer.
Now, if you want the energy, if you want the best energy, then you've got to go to the windiest places. And so what you try to do is get as many wind turbines in these windy spots as you could possibly handle. The trouble is that as you keep adding wind turbines to these spots, they interfere with each other. What happens is that the wind turbines in front, that is where the wind is coming from, rob the wind of the turbines behind. And so you have an effect that we call in the business array interference. This means that if you're trying to place wind turbines, if you have a piece of land where the wind blows strongly, you've got to decide what sort of arrangement you're going to make to do this.
AeroVironment's software program called Avenue allows wind energy companies to test different siting strategies without having to go to the expense of actually constructing and placing towers on their land. They can also compare and evaluate the wind power potential of different sites, allowing for development of those that would be most efficient. Improving the technology of wind energy production is the task of both private and government-funded programs. Under the auspices of the United States Department of Energy, SERI, the Solar Energy Research Institute, is a leader in technological development. Headquartered in Golden, Colorado, just outside of Denver, SERI researchers describe their latest achievements.
Probably the most recent R&D breakthrough that we've had is in the area of advanced airfoils for wind turbine applications. In addition, we've been able to put bigger rotors on the same turbines to capture more energy. In addition to that, we've been able to add some laminar flow characteristics so that you get improved energy capture when the blades get dirty and soiled, because we operate very close to the ground and there's bugs and debris that get on the rotors. And with this laminar flow feature, we can keep the degradation and performance way down, improve the energy capture. We've gotten something on the order of a 20 to 30% increase in energy capture through a combination of these advances in airfoil design.
And SERI maintains extensive on-site field testing facilities. In the desert sand of the San Gorgonio Pass, the latest ideas in wind technology can be tested under real-life conditions.
San Gorgonio, in our location, happens to have the largest array of wind turbines in the world, so this was a prime location to do this testing. So this facility that we're sitting in right now has been used primarily by SERI to gather data, to come up with various answers for yaw system problems, gearbox problems, brake system problems. We can take every component of the operation of this wind turbine, and we can take it from the source of the energy, which is the wind, and track every component on an individual basis to qualify its performance capabilities and so forth, and we can do it in conjunction with other components to make comparisons. And we can do that under different conditions. We also have the ability to remote control every turbine from inside of this facility so that we can artificially create different events which occur.
Results of the field tests conducted here are already being incorporated into newer, more efficient turbines. In the early 1980s, the primary motivation for funding and construction of wind farms was a lucrative tax structure. Federal energy credits and tax shelters brought forth an explosion in wind energy production. However, many of the early machines were hastily sited, poorly designed, or inadequately tested in this early 80s version of the gold rush. In 1982, fewer than 7 million kilowatt hours were produced in California. Tax credits and shelters expired in 1986, but curiously, the number of wind turbines placed online continued to grow. With carefully sited and soundly engineered machines, by 1990, California's turbines were producing over 2 billion